Good morning, guys. Welcome to chemistry. Today, we'll be taking measurements in precision, under which we have absolute and relative errors, accuracy and precision, significant figures. Now, what are measurements? Measurement is a process of determining how large or how small a physical quantity is as compared to a basic reference quantity of the same kind. And measurement is the process of finding a number that shows the amount of something, either how small that thing is or how big that physical quantity is. Components of measurement, we have the numerical quantity. This numerical quantity is the number gotten after measurement. We have the unit. Unit is a standard quantity used to express a physical quantity. In this case, we have milliliter. Then the name of the substance. In this case, it's water. Let's go to error. What are errors? Note, there is always an error in all measurements. It is very difficult to get an 100% accurate measurement. Whether you're measuring your weight, length, temperature, height, time, there are errors. We'll deal with absolute error, relative error, percentage error. Absolute error. The absolute error of a measurement is the difference between the measured value and the true value. Hence, the absolute value is the difference between a measured value and the true value of a quantity. The relative error is the ratio of absolute error and the actual value. Yes, this is called the relative error. The relative value tells us of the magnitude of the absolute value. And if the absolute value increases, the relative value increases. Percentage error is simply the relative error times 100%. The percentage error indicates how big our errors are. Small percentage errors indicate that we are close to the accepted or original value. Let's move on to calculations. Consider a table whose height is 98.2 centimeter. The measured height of the table is 98.2 centimeter. This was done to the nearest zero point 0.1 centimeter. Why? Because it was done to one decimal place. The actual length could either be smaller or bigger than 98.2. Now the measured length is 98.2. This might not be the actual length. There might be some error in calculation, and the actual length of the table might be smaller or bigger than 98.2, and this lies between the lower limit and the upper limit. What is a lower limit? A lower limit tells you that the actual length, that is the real length of the table, cannot be smaller than this number. The upper limit tells you that the real length of the table cannot be higher than this number. How do we get lower and upper limits? Yes, we get lower and upper limit by subtracting. For the lower limit, we subtract the absolute error from it, and the upper limit, we add the absolute error to it. Very important, getting our absolute error. Now, our absolute error is gotten by 0.1 over 2. The 2 is a constant. The 2 is a constant value, which gives us 0.05. This 0.1, remember I told you, for this particular measurement, it was done to the nearest. Why? Because it has just one decimal place. And to get absolute error, 0.1 over 2 will give us 0.05 as the absolute error. To get the lower limit, we subtract 0.05 from the measured value, hence 98.2 is the measured value minus 0.05 would give us 98.15 as the lower limit, and to get the upper limit we simply add the absolute error. Therefore 98.2 plus 0.05 gives us the upper limit. Moving on, we go to, let's take more examples. We have three experiments. We measured three lengths. The first one is 26 centimeter, the second is 26.0 centimeter, the third is 26.07 centimeter. To get the lower and upper limit, we need to look for the absolute error. For 26 centimeter, which is experiment A, we have 1 over 2. Remember, 2 is a constant. Why we place 1 there is because this particular experiment doesn't have a decimal place. It doesn't have a decimal place. It was rounded up to a whole number, and we use 1 over 2. This gave us an absolute error of 0.5. For experiment B, we have 26.0, which to get the absolute error is 0.1 over 2. Now 0.1 is because it has just one decimal place, therefore it was rounded up to the nearest 0.1 figure, and 0.1 over 2 will give us an absolute error of 0.05. Experiment C has two decimal places, and we use 0.01 over 2, giving us an absolute error of 0.005. To get the lower and the upper limit, is simply for lower limit, subtract the absolute error from the measured value, and the upper limit, add the absolute error to the upper value. Let's take experiment A. To get the lower limit of 26 centimeter, we simply minus the absolute error 0.5 from it, giving us 25.5. And for the upper limit, we simply add um, 0.5 to it, giving us 26.5 centimeter. Let's go to relative error and percentage error. Relative error is simply your absolute error over your actual value. Percentage error is gotten by multiplying relative error by 100. Moving on to the example we used previously, we're going to pick experiment B from the example. Finding the relative error of experiment B, we have our absolute error, which is 0.05, over the actual value, which is 26.0. This is giving us a relative error of 0.001923. To get a percentage error, we simply multiply this value by 100 to give us 0.1923%. Taking one more example, we have the temperature of a body is measured and recorded as 29.5 Celsius degree. Find the absolute error, the relative error, the percentage error. Note, the measurement is done to the nearest one decimal place. Hence, to get the absolute error, we do 0.1 over 2. 2 is the constant. This gives us an absolute error of 0.05. To get our relative error, is simply absolute error over actual value, which is 0.05 over 29.5, giving us a relative error of 0.001695. To get the percentage error, we simply multiply this answer by 100, giving us 0.1695 percentage. Moving on to the next subtopic, we have accuracy. As the word implies, accurate. Accuracy refers to how close a measured value is to the accepted value, which means values that are close to the actual. For example, we all know that the body temperature of a healthy human being is 37 Celsius degree, but a student measures it to be 39, 40, 45. Now, how accurate is that student from the actual value, which is 37 Celsius degree? That is what accuracy is. Precision of the order and refers to how close together a series of measurements are to each other. It is also referred to as a range of values. Let's take examples. Consider this dartboard. Consider this dartboard. Let's say the darts, the four darts are my values, are values I got from a measurement. Whereas the bullseye, which is the circle, the red circle at the middle, is considered as my actual value or my standard. Now, the darts are my measured value. In this example, the measurement is neither precise nor accurate. It is not precise because the darts are far apart from each other. Neither is it accurate because no, the darts are not hitting the bull's eye. The next example, now we have this. This measurement is precise. Why is it precise? Because the darts are close to each other, but it is not accurate because they are not hitting the bull's eye, which in this scenario is my actual value or my standard. To the next example, which is example 3, we see that this measurement is precise and accurate. Precise because the darts are close to each other and accurate because they are hitting the bull's eye. Yes, let's take one more example. For example, a woman steps on different scales to weigh herself. Her actual weight is 110 pounds. For the first measurement she had 132 pounds, 145, 107, 123 pounds. These measurements are neither precise nor are they accurate. They are not precise because they are not close at all to each other. They are far apart, and they're not accurate because they are not close or the exact value of the actual measurement we're looking for, which is 110. For the second one, she had 150, 149, 149, 150 pounds. This experiment is termed to be precise. Precise because they are close to each other, yes, but not accurate because none of them are close or the exact value of 110, which is what we're looking for. For the third experiment, she got 110, 110, 109, 110. Now, this is precise and accurate. Precise because the values are close to each other, accurate because they are close or the same as what we are looking for, which is 110. To get the range, to get the precise, you need to know the range. The range helps you know how repeatable these numbers are and how well it is possible of getting the same number when the measurement is repeated. The range is very simple to get, so this makes you know how repeated this no or how close together these numbers are or how repeatable it is when you do the measurement again. As to get the range, you simply take the highest number, which is 150, minus the lowest number, which in this case is 149, and we have a range of 1 centimeter. So you see that these numbers are 1 centimeter apart, which means they are very close to each other and they have a higher possibility of repeating these values when the measurement is done again. For accuracy, one of the ways to get a more accurate result is to do an average of the numbers you got. Hence, the number closest to the actual number is more accountable, which is more accurate. To get the accuracy, we just simply do the sum of the number over the number of numbers there, which in this case, the sum of the number is all the numbers added together over 4. The reason why we're using 4 is because we have 4 numbers there. We have 4 numbers there. And it's giving us an average of 109.75 centimeter. For the error tells you how much error there, like it tells you how much error, the percentage error tells you how much error there is in a measurement. The smaller the error, the smaller the percentage error, the more accurate the result is. So the smaller the percentage error, the more accurate the result is. And to get error, we have a formula for it, which is measurement, which is the measured value. In this case, our average minus actual. Actual is the actual weight, which is the real weight of the woman, which is 110 over actual times 100%. This is giving us 109.75 minus 110 over 110, giving us a value of 0.25% error. That means our error is very small, very, very small. It means that we are close to the standard, we are close to the actual value. Yes. Last on our board is significant figures. What are significant figures? Significant figures are the digits in the number that contribute to the accuracy and precision of that number. Not all significant figures are used to establish the digits that carry a meaningful representation of numbers, as not all digits in a number represent it. So not all digits in a number represent it. Let's go to rules, the rules for determining significant figures in measurement. Rule number one, please take notes. This is very important. Rule number one, non-zero numbers are significant. What are non-zero numbers? Non-zero numbers are any number that is not zero. So we have from 1 to 9, we have your 1, 2, 3, 4, 5, 6, 7, 8, 9. So anytime you see a number that is not zero, it is significant. It must be counted as a significant number. For example, 72.3 gram. In this measurement, we have three significant figures, which is the 7, the 2, and the 3. Now, let me give you a tip. What confuses students in significant rule or in significant figure are the zeros. The zeros are the problem. The non-zero numbers, when you see them, anytime you see them, whether waking up or sleeping, they must be counted as significant figures. What confuses students are the zeros, to know if the zero placed here is significant or this zero placed here is not significant. So follow me and closely. Rule number 2. Yes, captive zeros are significant. What are captive zeros? Captive zeros are the zeros that are trapped in the midst of numbers or in the midst of a decimal points. So captive zeros are in between numbers or decimal points and they are significant. So anywhere you see them, always count them as significant figures. For example, the measurement 800.4, this has four significant figures, which is your 8, your 0, and your 4. Rule number 3. If a number has a decimal point, trailing zeros are significant. Yeah. So what are trailing zeros? Trailing zeros are zeros that comes after something. And in this case, there are zeros that comes after a decimal point. So a decimal point makes zero significant. Hence, in this measurement, we have three significant figures, which is your 1, your 0, and your 0. Rule number 4. Yes, if a number has no decimal point, trailing zeros are not significant. So this is the counterfeit of rule number 3. Rule number 3 is telling you that when a decimal point is placed, the trailing zeros, which are the zeros that comes after the decimal point, are significant. But rule number 4 is telling that when there is no decimal point, then the trailing zeros, which are the zeros that comes after, they are not significant. So in this measurement, we have just two significant figures, which are your 1 and your 5. The last rule is rule number 5. Rule number 5 says leading zeros in a number are not significant. Leading zeros, whether there is a decimal or there is no decimal, any zero that comes before any zero that leads a number, all the zeros leading the number, they are not significant. And in this measurement, we have just two significant figures, which is your 7 and your 5. Let's take more examples. So if you can do this, but let's go to the correction. Yeah, so this is obeying, this is simply obeying rule number 2 to 4, 2 to 5, because in the first example, 200, remember we said in rule number 4 that when there is no decimal points, the trailing zeros are not significant, and there is no decimal points to make the zeros significant. Therefore, we have just one significant figure, which is 2. In this, the same thing applies for the 3,500. The same applies for the 700,000. So where zeros are and there's no decimal point, like where there's no decimal point and you have zeros, trailing zeros, the zeros are not considered to be significant. Now let's look at this example 4, 20,001. The zeros in between, the trapped zeros, remember rule number 2, they are significant. Why? Because they are trapped in between numbers, hence they are significant. Therefore, in that rule number 4, we have 2 as a significant number, 0, 0, 0, and 1. Therefore, we have 5 significant figures. Let's go to other examples. Let's deal with decimals now, and let's take the correction. So remember, I told you that for the first example, which is 200 points, it's telling you, I told you that zero, this is a trapped zero also. It's obeying rule number 2. Trapped zeros are significant. Trapped zeros are zeros that are trapped in between numbers or decimal places. They are significant. Hence, the first one has 3 significant number, which is 2, which is 0, and 0. The same goes for the second one, the third one. Then look at the fourth and the fifth one. Remember, I told you that anytime you see a leading zero, be it whether there's a decimal point or there's no decimal point, the leading zeros are not significant. And for example 4, 7, we have just one significant figure, which is 7. And for example 5, we have just two significant figures, which is 2 and 0. So let's take more example. Okay, these are more emphasis. This is telling you that leading zeros are not significant and every other figure is significant. So take a good look at it and study it. Also, this will give you more would give you more emphasis on it. Remember, leading zeros are not significant. Then we have, in this case, we have just 4 significant figures, which are the 5, the 0, the 9, and the 0. So thank you very much for watching, and stay tuned for the next video.